All right, this is the seventh video in the probability section. This one is combinatorics again, but with replacements. So you can imagine where we had balls and urns before, and we took a ball out where we didn't put it back. We actually put it onto into a row and onto a template. This time we're actually going to put them back. So it does change the maths a little bit. So let's have a look at this example and see what that does. And urn has 6 red balls and 4 green balls. 8 are extracted with replacement. What is the probability of getting 5 reds? Okay, so this what we're going to do here is we can imagine if we're putting them back, then I want to record it, don't we? So let's imagine that what we do is we just write in horizontally the result of the extraction, red or green here. So that here's 8. This particular arrangement only has 1, 2, 3, 4, 5 reds. So that would be a kind of a success in the sense of this trial. Okay, so we're putting them back. Okay, so each time we take one out, then they have the same probability. So if there are 6 red and 4 green, 10 in total, then the probability of extracting a red is going to be 0.6 every time we pull one out. Okay, so we're going to do that. We're going to draw it out. We're going to got it as a red. Then we're going to put it back, pull another one out, and that's a green. And then we're going to put it back, pull another one out. That's a red. Put that back. Do another one. That might be the same. Actually, the actual same red, but it doesn't matter to us. Yeah, it's just a red, and so on. Then we go through the process and extract that 8, and then we've got a result like this. Now this one has got 5 reds, but other trials may not have 5 reds, some different number. And what we want to know is what is the probability of getting 5 reds. Okay, well, when we're looking at this, what we're actually saying that the probability of getting 5 reds and 3 greens, because the probability of a red is 0.6, a green is 0.4. So the probability of just getting 5 and 3, as it were, would be that's of any particular arrangement. So this arrangement here would have a probability of 0.6 to the power of 5 times 0.4 to the power of 3. And we would say 0.6 times 0.4 times 0.6 times 0.6 times 0.4 times 0.4 times 0.6 times 0.6, wouldn't we really? But of course, that just rearranges like that. But what we've got to consider is that there are actually lots of different arrangements of getting that. So not only is the 0.6, 0.4, 0.6, 0.6, and so on, but the various other arrangements which we can simplify as that. How many arrangements? Well, we did that in the last video. That's 8 choose 5. So that's 8 factorial divided by 5 factorial times 3 factorial. So that number. So then the total, and these are mutually exclusive, so we can add them up. So we're adding up that many lots of this. Okay, so in other words, it's that times this. This 8 choose 5 is the binomial coefficient. And we can easily work that out. This is a sort of identical question, really. If I flip a bias coin that has a 0.6 chance of a head, I do 8 flips. What's the probability of 5 heads? Well, same thing, isn't it? Here we've got heads, tails instead of R's and G's. but our 0.6s are the same, our 0.4s are the same, and this is the answer here. Now, this bit, this 8 choose 3, we call the binomial coefficient. Why is it binomial? Well, it's binomial because it's 2. It could, we're looking at a situation where we can have one or the other, a head or a tail, or a red or a green, or whatever. So that's what makes it binomial. And interestingly, these numbers, as we increase this one here, 3 here, 8 choose 0, go, let me try 8 choose 1, 8 choose 2, 8 choose 3. They sort of you might see these kind of go, the numbers going up and then coming back down again. Let's just have a look a bit further at that. Okay, so this is what we've got. So so if we think about it in terms of the probability tree, yeah, you could draw a probability tree for this, couldn't you? But you've got 8 levels of branches. All right, there's only 2 events come off each node, but I mean, you got a lot of different possibilities there, haven't you? So, but that essentially is the number of leaves, and of course, the number of leaves that we are interested in, that we've got 5 reds and 3 greens. So that is another way you can think about this particular problem. When we talk, incidentally, when we're talking about binomial coefficients, we tend to talk about trials and we talk about successes. So if we can have the same thing if we're throwing darts at a dartboard. If we hit the ball, that's a success. Might have a probability of 0.1, and that's the sort of the terminology we use. Okay, so let's just look at this last bit here. If we ask the same question with no heads, 1 head, 2 heads, 8 heads, each has a different probability. So what is the probability of, with this this biased coin, this unfair coin? What would be the probability of getting no heads out of 8 flips? Yeah. What would be the probability of 1 head, and so on? Well, we can work these out. It's similar to this. Obviously, this is going to be that's 8C, should be 8C3 or 8C5. So we can actually work that out, and then we get a whole set of numbers. Well, there's 9 different possibilities. We can have no heads, 1 head, 2 head, all the way up to 8 heads, couldn't we? You'd think that no heads would be quite unlikely. 8 heads would be quite unlikely, even though it's a biased coin. Somewhere in the middle is going to be the most likely. Well, exactly. Well, if we look at this graph, that supports that. This actually goes to slightly different numbers involved here. Here we've got 20 trials with a probability of success of 0.25. So, and this particular one here, 20 trials, each success on its own is a probability of 0.25. So we can graph all those, and these are the probabilities that we would get. So this shape is basically the binomial distribution, which we'll get to when we're doing the statistics section. We'd expect, I mean, we're doing 20 trials, probability of 0.25. We would expect 5 successes would be the most likely figure. That's sort of borne out by this, isn't it? The bar for 5 successes is the highest. So, yeah, it supports that idea. We kind of also find with these things that the lower the p-value, the more skewed it is to the left. It rises up quickly to the left and then tails away to the right. And then if p was a higher number, like 0.75, that would be the other way around. It would rise up slowly up here and then tail away fairly quickly. So this is the binomial distribution, and it represents the probabilities of successes, and which we can apply coin flipping, balls out of bags, with replacement, and various scenarios. So so that is that. So that's the end of the probability section. Or obviously there's examples videos to go and have a look where these things are illustrated in greater detail. But yeah, hopefully you found that all very useful and interesting, and I'll see you next time.